Alright, welcome back everybody. In this video we're going to look at how we find the lengths of polar curves and a few examples related to that. We start here with the formula for the length of a polar curve, and I'm missing a d theta here. So to find the length of a polar curve, it's going to be the integral from alpha to beta of the square root of r squared plus dr d theta squared d theta. And I would say that this is a formula that's worth remembering in order to find the length of a polar curve. We're going to look at the derivation of it, and you'll see how long it takes us to derive this formula. And it gets a little sketchy for us as far as deriving it every time we want to use it. So we're better off. This is a formula that we're definitely better off knowing. But let's go ahead and we'll derive this formula and see where it comes from. We start with the idea of using the parametric formula for arc length. So we're taking the arc length from alpha to beta of the square root of dx d theta squared plus dy d theta squared with respect to theta. So that's our starting point here. And remember that when we have a parametric formula, x is equal to r cosine of theta, and y is equal to r sine of theta. And so, dx d theta, the derivative of this with respect to theta, is negative r sine of theta plus cosine of theta dr d theta, and dy d theta is r cosine of theta plus sine of theta dr d theta. And so, substituting these values into our arc length formula, we have the integral from alpha to beta of the square root of dx d theta squared plus dy d theta squared with respect to theta. And now we've got to expand out these two squared quantities underneath the radical. And so this turns into the integral from alpha to beta of the square root of, hope I don't run out of room here, we've got r squared sine of theta, r squared sine squared of theta, minus 2r sine of theta cosine of theta dr d theta, plus cosine squared of theta dr d theta squared. Then we expand the second one out, and we've got r squared cosine squared of theta plus 2r sine of theta cosine of theta dr d theta plus sine squared of theta dr d theta squared. Come on. All with respect to theta. Now, you should notice looking at this that these two terms cancel each other out. And then I'm going to regroup the terms a little bit. I'm going to regroup them so that I have forgot my radical sign. Regroup them so that I have r squared sine squared of theta plus r squared cosine squared of theta plus cosine squared of theta dr d theta squared plus sine squared of theta dr d theta squared all with respect to theta. And now I'm going to factor out some things within these little pieces. From the first two terms, I'm going to factor out an r squared. R squared times sine squared of theta plus cosine squared of theta. And from the second two terms, I'm going to factor out a dr d theta squared. And our old buddy Pythagoras is calling again. These sine squared of theta plus cosine squared of theta are equal to 1. And so this turns into the integral from alpha to beta, the square root of r squared plus dr d theta squared with respect to theta. And there's where that formula comes from. All right, let's go ahead and use that formula in some examples. We'll start with determining the arc length of r equals theta from 0 to 1 for theta. So that's going to be the integral from 0 to 1, the endpoints of our angle interval, the square root of r squared. R is equal to theta, so that's going to be theta squared. And dr d theta here is just going to be 1. And so there's our formula for the length of this curve. And so I'm going to go ahead and integrate that. The integral of the square root of theta squared plus 1 squared with respect to theta from 0 to 1. And the length of this arc is 1.148. It's a whole lot easier than, writing x equals theta cosine of theta and y equals theta sine of theta and then differentiating those and setting that whole formula up. It's a whole lot easier to know this arc length formula and just be able to substitute into it. Alright, next one. Determine the length of the curve r equals 1 minus cosine of theta. Now notice in this, they don't give us limits of integration. So we're going to have to figure out what those limits of integration are. But our integrand is going to be the square root of r squared plus dr d theta squared. Dr d theta here is going to be, 0 plus, it's just going to be sine of theta. And now we need to figure out what our limits of integration are going to be. And so we'll look at the curve r equals 1 minus cosine of theta. And I graph it from, I'm going to put a tracer on this, graphed it from 0 to 2 pi. And that looks like we've got the whole curve when we do that. Zoom in on this. Starts at 0, gets to the end of the curve at 2 pi. And so we're going to integrate this from 0 to 2 pi. That gets the entire curve. And so now we'll go back to our calculator and go ahead and integrate this. It's going to be the integral of the square root of quantity 1 minus cosine of theta, quantity squared, plus quantity sine of theta, quantity squared, with respect to theta from 0 to 2 pi. Uh-oh, what did I do? I forgot to close my square root. Let's try that again. And we get that the length of this curve is 8. Alright? that's where we're going to end this video. We'll come back next time and look at surface areas and examples 3 and 4. See you guys then. Have a great rest of your day.